in a bunch of different domains. Yeah, in a bunch of different domains. I've worked for many years, and I've got a lot of research inspiration from robot soccer, where there's teams of independent agents trying to score goals, like shown here. If you haven't been to
Hi, it's Carissa. The Robot Soccer World Cup final.
If you haven't been to a RoboCup competition, I strongly encourage you to come. There's lots of different leagues. This is the standard platform league from several years ago. Our team in this video is the one with the arms behind the back. We're playing against a team from the University of Bremen in Germany. And in these, the robots have to execute. They have to walk and kick and see. They have to perceive. They have to coordinate. They have teammates. They have adversaries. And it's a great domain for multi-agent learning, and for multi-agent coordination in general. The challenge gets different, harder every year. So this was back when there were 14 robots on a team. It's now a bigger field with 5 robots on a team, and a black and white ball and white goals instead of color coded. So that's, we sort of raise the bar every year, with the goal being in the long term to have a team of humanoid robots that can beat the best World Cup soccer team on a real soccer field. The next competition is at University of Eindhoven in the Netherlands next summer. And if you haven't been, you really ought to go and see what it's all about. Another domain that's inspired a lot of my research is general purpose service robots. So if you come to my lab, you'll see robots like this one wandering around the hallways unattended. This particular video was about some grounded language learning, but we have these robots trying to do activity recognition, multi-robot navigation. If there's 2 of them coming down the same hallway, how do they pass each other? All of these are, and we want them just to be able to be on for long periods of time and become generally capable. It's another great domain for multi-agent research, where some of the agents in that case are people. And then, as with many, I've been very inspired by autonomous driving. I had a car in the DARPA Urban Challenge back in 2007, pictured here, and I've thought a lot about what the world will look like when all the cars on the road are autonomous. Instead of using traffic signals and stop signs, trying to have intersections that look like this one. And this is when all the cars are autonomous, but we've thought about a lot about what if there's mixed human drivers, autonomous drivers, and things like that. And then most recently, something I've been very excited about, my team at Sony AI created an agent, GT Sophie. Like one of these, this one in this picture is one of them. The colored agents in the slides I'll show you here, the white ones are driven by people, the colored ones are driven by our agent. We had a paper that appeared on the cover of Nature about a year and a half ago, based on creating a end-to-end deep reinforcement learning agent that can beat the best drivers at Gran Turismo high-speed racing in simulation. And the success, like in the successes in chess and Go and Jeopardy and poker, there was a lot of computation involved, lots of data, but also top-notch engineering and a few algorithmic and methodological insights that we talk about in the Nature article. I also have some talks explicitly on this online that you can see if you'd like. But for those of you who aren't aware, Gran Turismo it's a very high fidelity simulator. There's a movie out right now called Gran Turismo that sort of documents a person who learned how to drive in the simulator and then used that experience to become a professional race car driver. It models things like slipstream, airflow, traction, effects like that. And it looks a lot like this. This is a race of all people, but we the interface to the car is brake and throttle and steering at 10 hertz and trying to come up with control that will do better than people, given a rich sensing environment. And back in 2021, we raced against 4 of the top people in the world, people who have put in their 10,000 hours to become real experts on 3 different racetrack and car combinations. And the people won in July. When we had a rematch in October, we were able to win. And if I were going to go on to now give a full talk on this, I'd launch into the approach and talk about how we did race car control and tactics and racing etiquette. but the main point is that it really was end-to-end deep reinforcement learning. That's it. The agents started off randomly, running into walls, running off the course, and a week to 10 days later, got superhuman performance, not just on an empty track, which is hard in its own right, but on the rich multi-agent interactions that come up in racing. And this video sort of shows one of my favorite types of episodes or skills. You'll see two human drivers in white here and two GT Sophie agents in green and gray. They're sort of indicated on the right here panel as well. And you'll see this sort of double crossover where they sort of let themselves get into a position where they're behind the human drivers, but in a position where around the turn they're going to be able to come out in front. And so that's known as a crossover pass, and they do things like also slipstream passing and all sorts of stuff like that. So there's a lot more that can be said about that. Like I said, there's a lot of details in a dedicated talk on my website. But what I want to talk about today is teamwork, and that's the theme of this, and the multi-agent learning aspects. One of the themes of the workshop. And then human teamwork, often people practice together and become, sort of a well-knit team at search and rescue or whatever they're doing together. And a sort of traditional scenario for robots also has been pre-coordination, where there's, the robots or people are given protocols, common languages, they can train together. There's a long history of ways of making this happen in the multi-agent systems community. And even back in 2001, I had a paper with Rich Sutton and I used the keep-away domain for fully decentralized learning. So these red agents were each learning on their own to where to pass the ball and where to go. In a game of keep-away, they were using reinforcement learning, but each independently training together with a little communication in this case, but not very much, and ending up learning the task quite well. And so that's going to be the framework or sort of the setting for the main contributions of this talk, where there's agents that can train together, but they're not centralized in any way. They're learning independently. Before I launch into that, though, I just also want to briefly say that we can even go beyond that. I've done a lot of work in the last decade and a half or so on ad hoc teams as well, where they don't even get to train together. There's you're having to try to coordinate with an unknown teammate that's programmed by others that you may not be able to communicate. They're going to be suboptimal. So just like people can pick up soccer with people they've never played before, or pick up basketball, have never played with them before, you just jump on and start figuring out how to work as a team. We'd like robots to be able to do that as well. In like a search and rescue scenario where if there's a disaster, we can all bring our robots, and without having to reprogram them, they would all sort of band together to become a team. And I've been very pleased to see that there's a nice growing community of researchers on ad hoc teamwork, where the challenge is to create a single good team player. But rather than focusing on that, I am gonna zero in on sort of the technical details of a paper, like I said, that appeared at AAAI called DM Squared. For decentralized multi-agent reinforcement learning via distribution matching. Just one more vignette before I do that, though. I'm calling an audible a little bit here based on the previous few talks, which I found quite interesting. I just wanted to also let people know about some relatively old work from my group on some theoretical guarantees. This was Doran Chakraborty's thesis from a long time, from about 10 years ago now, on convergence, targeted optimality, and safety in multi-agent learning. It was the first example of agents that in an n-player, n-action game would converge to a Nash equilibrium with probability 1 in self-play. So if they're all using the same seamless, that we called seamless algorithm. And that if they were playing against a memory-bounded agent, one that's sort of playing best response against their actions in a sort of fictitious play kind of way, that they would achieve targeted optimality, meaning that they could optimally exploit any agent that's a member of that class, so that target class, namely of memory-bounded agents. And then the third property that it held was that it was eventually against any other agent, one that's not a part of that target class, that's not self-play, that you could achieve at least the maximum payoff. And the high level view was that there was sort of a staged version where first you try to identify whether you're in self play, and if so, you can just converge to the Nash equilibrium. If not, then you try to identify whether the agent is in this target class of memory bounded agents, and if so, use a reinforcement learning algorithm to try to figure out what the best response is to their strategy, and otherwise just fall back to the minimax strategy. So not going to go into the details of that either, but just to say you can find it in a Johannes article from 2013. It first appeared in ICML in 2010. But really, the main event in this talk is a paper that appeared in AAAI called Decentralized Multi-Agent Reinforcement Learning via Distribution Matching. The first author is Caroline Wang, actually three co-first authors, but Caroline Wang is my current PhD student, and Ishan Durgkar and Elad Liebman are former PhD students. Ishan's now at Sony AI, and Elad is at Spark Cognition. And this is in the multi-agent reinforcement learning setting. And there, as I think you all know, there's several different coordination sort of settings within multi-agent reinforcement learning. It is possible. The simplest, most straightforward way is to do fully centralized learning. In some domains, that's possible, where you can learn a single policy that comes up with a joint action for all of the agents. But that's not always possible. Sometimes there's going to be enforced decentralized execution, where the agents are going to have to make their own decisions. But sometimes, even when that's the case, you can have the benefit of centralized training, where they can practice together and have a sort of shared utility function, and then only have to be decentralized at execution time. And there's been a really interesting thread of research on CTVE, as it's called. And then you can also go one step further, where there's decentralized learning, but there's sort of a dedicated communication channel to facilitate it. But these all require sharing model components or require communication, just like that simulated soccer keep away I showed you. We'd like to be in this setting where we can foster team cooperation without any explicit communication. And sometimes, this isn't to say that if there is communication, you should use it. Last time I gave this talk, someone asked, why wouldn't you use the communication if it's there? And I think, of course, you should. But there are situations where the agents don't have the ability to communicate, or they can't do centralized learning. So we need to be in this fully decentralized setting. I think the search and rescue robotics example is apt, and so is autonomous driving. You might need to do this for scalability or parallelism. So that's the goal. That's the setting for this work. And what we present is a new algorithm that enables cooperation in this decentralized setting. The one assumption we do make, so this is the extra assumption we make, that makes it possible for the agents not to, as their, the fundamental challenge here is that each agent would be moving on its own or deciding what to do on its own. And if there are multiple Nash equilibria in the game, or multiple equilibria, they would have a hard time coordinating on which one they're trying to reach. And so we assume that there is some expert team demonstration that they all have access to. So they have this sort of shared experience that they've all seen a team do this task. And then they're going to try to use that as the way to break symmetry, and have each agent sort of imitate one of the members of from this expert team demonstration. So the contributions of this work: it's a decentralized multi-agent reinforcement learning algorithm based on distribution matching to encourage coordination. I'll explain that in a second. We have a theoretical analysis that shows the conditions under which DM squared converges. It's the case that it also that we can say that they go to a Nash equilibrium, even if they're not only trying to do imitation learning, but also trying to learn from the environmental reward with a sort of a mixture of the two. And then there's an empirical validation. So the setting is probably a familiar one to most of you. It's stochastic games. There's a set of agents, a state space, an action space, an initial distribution, a transition function, a reward function, that are both joint transition and action and reward functions. So depending on all the actions of all the agents, and we need to learn a per agent policy. Each agent I needs to learn its own mapping from states to a distribution over actions. And the distribution matching approach is sort of one of the sort of relatively recent ways of doing imitation learning. And we assume that there's, as I showed in the previous slide, that there's a per agent state action visitation distribution that they can use to try to match, that each agent tries to match that visitation distribution to find a policy that leads to a state action visitation distribution that's the same as as the expert that they're imitating. And so, you know, the sort of cartoon example of this was if there's an agent in a two-state Markov decision process that's acting randomly, it's going to visit states 1 and state 2 in this MDP equally often. But if it's trying to match an expert that has this sort of green distribution where it's in S2 a lot more than S1, then it's going to change its policy until it finds that you know, that it's doing more of the self loop in S2 and more of the change, you know, the action that moves from S1 to S2 when it's in S1 until it reaches the same distribution. And that's the way it does its imitation. So to take this to the you know, to the full multi-agent setting that we're interested in, we assume that there's a set of experts that's been trained together, and I'll talk more about that later. It's important that they have been trained together. They don't have to be optimal. They can have a suboptimal policy, but they have to have been trained together. Each one induces a state action visitation distribution. Each of our agents in blue is assigned one that it's trying to find a policy that matches its expert distribution. And then we actually show that that if they do this, that if they follow this paradigm illustrated on the left, that it leads to agent policies converging to compatible expert policies. And that it remains in Nash equilibrium even if we mix in a weighted amount of the environmental reward. And in the paper, there's full pseudocode. I'm not going to walk through it in this talk, but it basically implements what I've illustrated on the left here. And then in the paper, there's also a bunch of experiments, and they're in the StarCraft 2 environment, and it's a cooperative, fully cooperative setting. So there's in one of these, there's 5 agents who are having to learn independently to fight against 6 hand-coded or fixed opponents, and another it's 3 of them learning against 4. And these are sort of standard parts of the SMAC benchmark. And then we compare against a bunch of different baselines. So the fully decentralized learning, where there is independent PPO, where they're each just learning using their own instance of PPO. That's you know, the problem there is that they could be very uncoordinated, and they could each go to different sort of equilibrium solutions. And then we also have some sort of what we would think of as upper bounds, QMix, two CTDE algorithms, standard CTDE algorithms, that have the benefit of centralized training. So which our agents don't. So we would expect not to do quite as well as those. And then we look at different DM squared experts that they train with. The experts are state-only demonstrations sampled from different checkpoints along either QMix or IPPO processes. And so in particular, not optimal. They're at different checkpoints along the learning curve, and we'll show what happens with different qualities of experts. And so we have 2 sort of types of experiments here. We first compare against the baselines. So here, the bottom sort of brown line is IPPO. So again, that's where there's no coordination at all. And then the upper lines on both of these graphs are the CTDE algorithms. So they have this extra centralized training that's not available to our algorithm. And then here's DM squared, sort of a version of DM squared that doesn't have the benefit of the expert. It's doing self-imitation learning. So it's just, rather than using an expert, each agent is just copying its own most successful trajectories in the past using the SIL methodology. And And that can do well if they happen to sort of hit on the same equilibrium, but it's inconsistent. So in this on the graph on the right here, it does horribly because they each end up going in a different direction. And so that's sort of that motivates the need for them coordinating based on the single expert demonstration. And when they do that, these two lines are with either a sort of an early checkpoint, or which is the darker line, and the lighter line is with a later checkpoint, as shown by the dashed lines here. And you'll see that learning, they end up learning to outperform the experts that they're copying. When they do the copying, by the way, the imitation, they're using GALE, generative adversarial imitation learning. And then we have a final line here that I'll show that where even though our agents are learning with IPPO, the demos that they're copying were learned with QMix. So even with different learning algorithms for the experts versus the learners, they still do quite well. And then the other style of experiments, just to wrap up, is an ablation. We were interested to see how important it was that the expert demonstrations that the agents are keying off of were trained together, so trained jointly. And that's one sort of thing that we can vary. They can either be trained jointly or they can be in the same domain but trained separately. And then the other is, are the policies taken from the same run of this expert? Is it a concurrently sampled policy for each of the experts that's being copied or not? And so those are the ablations we did. Here's the sort of full DM squared method. And it turns out that the first ablation, if they're jointly trained but not concurrently sampled, it still does almost as well. But if they're not jointly trained, then things look much worse. And so it turns out that it's very important that the team of experts that they're using it has been trained concurrently, and that sort of makes sense. It suggests that team of experts will have hit on some equilibrium strategy, and that's what's being used as the coordination signal for the imitating team. So that's basically what I wanted to get across here. Full details are in the AAAI 2023 paper with this set of co-authors, and with that, I'll be more than happy to take any questions.
You have time for some questions.
I have one question in the when you're matching the distribution with Gale. Are there any explorations on what happens if there's a bad sample from the QMix trained or the IPPO trained policies? Have you considered how you would deal with that if that exists?
So by bad sample, I presumably you mean like a suboptimal actions or something like that.
Right, that's suboptimal action.
Yeah, and that's exactly why we did these in this slide, where we have the expert that was trained from the 5M means it was trained from 5 million time steps of IPPO, which was not enough to converge to optimal if it's using IPPO. Remember that this is that the IPPO line is the brown one here. So and so it is very suboptimal, and then we have also the IPPO demo that's a little better, the 7 million. So there's no claim that they're actually acting optimally, and still if we use Gale on them, we're imitating them. It's fine. I think that the intuition here is that what's being learned from the experts is not optimal behavior. In fact, that's being learned from the environmental reward. What's being learned is the coordination. It's a sort of a way to break symmetry so that they, if there are multiple possible strategies or equilibria, that they each play their role that the experts did, even if the experts aren't optimal. So I think that's, having suboptimal actions from the experts empirically here is not a problem.
Thank you.
Thank you, Peter. Any other questions? Yeah, sorry you weren't here in person, but if you would see, there's almost a full house here to listen to you. So thank you so much for taking the time.
Great. Yeah, I'm very sorry I couldn't be there. Thank you anyway
worries.
for including me, and thanks a lot for organizing the workshop.
Thank you. Let's give Peter another.